Hello, my name is Anthony, and this is my Lab 4 report. The purpose of this experiment was to measure the actual values of conventional current and potential difference in circuits, as well as looking at the behavior of resistors and capacitors. The fundamental physics principles included the node rule, which is that the current is the same throughout an entire circuit, and the loop rule, which is that the potential difference of a loop of a circuit is equal to 0. There are also two equations we use, which are the capacitance and resistance equations shown at the bottom. The model I used in this lab is the Colorado FET circuit construction kit, and the main results were that the change in potential across a circuit is 0 volts. Increasing a light bulb's resistance increases the amount of time it stays lit in a circuit with a capacitor, and the experimental RC value was 5.98 seconds. Using the initial conditions given in the lab instructions, I set up the circuits in the Colorado FET model. Though I also used the model's measuring tools, including ammeters, voltmeters, and stopwatches, to collect data. And throughout the experiment, the system was the circuit, while the surrounding was the earth. Also, I assumed that the wires and measuring devices being used did not cause a change in electric potential or current of the circuit, and I used these assumptions to simplify the calculations, but also because the experiment was taking place in a model. First, I set up the circuit shown on the right with the initial condition that the batteries have 1.5 volts each. Then, using the loop rule, current rule, and the resistance equation, I predicted the current of the circuit to be 0.0204 amps. The ammeters recorded a current of 0.02 amps, which was close to my prediction, and when the ammeter was reversed, it recorded a current of negative 0.02 amps. Then, I replaced one of the ammeters with a voltmeter, and the voltmeter read 3 volts because the potential difference from the batteries was 3 volts and the resistors were not in the circuit, so they did not create a change in potential, and the ammeter read a current of 0 amps because the circuit was not closed and therefore there was no current. Then I closed the circuit and calculated the potential difference of each of the sections shown in the image. All of the sections were equal to 0 volts except for the 3 sections listed which had the voltages shown. Then I graphed the potential difference across the circuit, and we should expect that the potential difference should be 0 across the circuit, which is also shown in the graph, and when you add all the potential differences together from the experiment. Now I created this parallel circuit, and the current increased. This is because the change in potential around the new loop must still be 0 volts. However, the new loop only uses the first resistor. So this means that there must be an increase in current so that the change in potential still equals 0. Using the resistance equations and the values found in the experiment, I was able to calculate the resistance at every part of the circuit as shown. For the rest of the experiment, I used these two circuits shown, which have the initial conditions of a 9-volt battery and a 200 mF capacitor. For both setups, the bulb started shining and continually dimmed until it stopped shining. As well, the current slowed down for both setups until it stopped. However, the current moved in opposite directions for the two circuits. Then, using a 10 ohm bulb, the capacitor charged and discharged in 6.4 seconds, while it charged and discharged in 10.7 seconds with a 20 ohm bulb. This means that increasing the resistance of the bulb increases the amount of time that it stayed bright. Next, I calculated the RC value using the right circuit from 2 slides ago. I also used a 30 ohm bulb. I calculated the model RC value by multiplying the circuit's resistance by capacitance, and that gave me 6 seconds. And for the experimental value, I calculated the potential difference of the capacitor every second for 20 seconds. Then, using this equation, I was able to graph the data in such a way that the slope of the graph is equal to -1 over the RC value. And this gave me an experimental RC value of 5.98 seconds. To answer the first what-if questions, the ammeters being used in real life would have caused a slight potential drop in the circuit, and this would have meant that the ammeters would have recorded a slightly lower current in real life than in the model. For the second what-if question, if I connected a capacitor to a battery in the model, it would predict that the capacitor would become fully charged instantaneously. However, in real life, it would become fully charged quickly, but nowhere near as fast. This is because the circuit in real life can only handle so much current at a time, and especially cannot handle large instantaneous changes in the amount of current, which the model predicted. In conclusion, my model RC value was close to my experimental RC value, but they were not identical. While both the experiment and the model used the same system, the same circuit, and initial conditions, the model calculated the value by simply multiplying the circuit's resistance and capacitance values, while the experiment used the change in potential difference over time to graph it and find a relation. Furthermore, there was some experimental error in the experimental value, and that was due to human error, because I was not able to always stop the experiment at exact seconds, so the potential difference were usually slightly off. However, overall, the experiment found good approximations for the RC value.